Let me introduce you to the audience. Okay. Okay, the next talk is from Giovanni Jona-Lasinio from the Università di Roma. And you know that the research activity of Giovanni Jona-Lasinio has been in theoretical and mathematical physics and concerns a wide spectrum of topics. He's widely known for having constructed with Nambu the first model in elementary particle physics with spontaneous symmetry breaking. He also did the first introduction with Carlo Di Castro of the field theoretical renormalization group in the study of critical phenomena, and has developed recently a theory of stationary states far from equilibrium. I think Giovanni Jona-Lasinio is going to talk us on quasi-static transformations of diffusive systems, renormalized work, and all that. I think Giovanni, please, you may begin your talk.
I can start.
Yes, thank you very much for being here.
Thank you very much for your invitation. And maybe I see too many people. So they cover part of, I don't know, you see the full screen of my presentation.
Yeah, we can see your full screen.
Okay.
Gianni, yeah.
So well, just the title, just a citation of a well-known book by Streeter and Whiteman, Spin and Statistics and all that. So what I'm going to talk about today is about quasi-static transformations for diffusion systems, which are the system which have been the subject of the so-called macroscopic fluctuation theory, and on which I've been working for the last more or less 20 years. Today I will not. I will develop some remarks on that I've been thinking about lately, about these transformations for this diffusive system. Okay, so well, I hope you have read the topic, the abstract, and the considerations I'm going to develop have been inspired by reading some memoirs of Clausius, but I will talk about Clausius if I have time at the end. You see, that has been one of the advantage of the lockdown, that you could read the many things that
Gianni, I think that the connection is not good. Just wait a moment to see if it recovers at some point. Let's see if oh, okay, se ha ido. Bueno, sorry about that, but we are going to try to reconnect Jonah. You should unmute, please, Jonah.
Yeah.
Okay, now, right now. And you have to...
Now you can see the
No,
slide?
not the slides, no, you have to share again your... Sorry, but connections are not perfect, not yet. Okay, here.
Okay.
Okay, you may... The first things that you said, maybe we didn't listen it. Then maybe you can restart if you wish.
I have to restart, it's better.
Yes, I think so.
Yes, okay. So, I mean, the remarks that I'm going to develop in this seminar or webinar have been inspired by reading some memoirs of Clausius. I will speak of Clausius if I have time at the end of this seminar. But that has been, if you want, one of the advantages of the lockdown, that one has had time to think about to read many things that otherwise would be postponed. You see, the existence of entropy in classical equilibrium thermodynamics implies that this integral dq delta q over t does not depend on the particular reversible quasi-static transformation joining to fix point initial and final, to fix the initial and final states. So in the simple case of an ideal gas, you have this one form, which is an exact form, that you can write also introduces a parameter. Well, this pair of functions, the couple temperature and pressure, describes path in this TP plane. And this integral does not depend on the particular path we can choose, we choose, but only on the initial and final state. Okay, so the question was, is it possible to have a similar situation in some non-equilibrium situations? Or now, I think that what we have seen in the last 20 years, that diffusive system for which we have microscopic models of lattice gases is a class of systems for which there has been much progress. These are, in fact, the systems which are the subject of the microscopic fluctuation theory. And among the other things, one thing that my group, and I will give you the reference later, we have developed is a theory of quasi-static transformations. The question of quasi-static transformation was raised long ago, even in thermodynamics books, like that of Cullen, in which he observed that it cannot be a sequence of equilibrium states because in ordinary thermodynamics, because you otherwise nothing would happen. You have to go a little bit out of equilibrium. And we tried to understand this aspect of going a little bit out of equilibrium for this class of systems. So in our approach, a quasi-static transformation emerges as a continuous succession of stationary states modified by 1/tau corrections. This tau parameter is essentially a time which is large with respect to the relaxation time of the systems. And from this analysis, we obtain two exact expressions connecting the equilibrium entropy or free energy or its derivatives to deviation from stationarity which follow from a systematically follow development of hydrodynamics in powers of 1 on the in general, I mean, the equilibrium free energy, we shall suppose that this has a density. This is natural as an equilibrium state can be inhomogeneous, so that it can be evaluated on any profile, even in non-stationary profile. And so the free energy has these forms as the integral of a space of so we consider a typical situation, which is a system in contact at the boundaries with at least two reservoirs, and in presence of external field acting on the bulk. We shall assume that the macroscopic dynamics is described by hydrodynamic equations associated to conservation laws specified by constitutive equations, which locally imply equilibrium and linear response. So we consider far from equilibrium situations which are built up from small deviation from equilibrium at each point of time or space. So let me describe the setting, which however is quite standard. So we we have a system which is on its surface is connected to reservoirs. It can be many or even a continuous distribution of reservoirs, and then which are described by chemical potential lambda, and under the action of an external field. So, and the assumption is that you can describe the system completely by hydrodynamics. So you have a conservation law and an expression for the current, which is given by the constitutive equation. And the hypothesis is that this constitutive equation is local. So for diffusive system, this is the expression. So you have a gradient part, a gradient of thermodynamic rho indicates a generic thermodynamic variables. These are diffusion coefficients. So the hypothesis that you have small gradient locally, and then you have a mobility which describes the reaction of the system to the external field. So you have an equation, which is a parabolic equation that describes the hydrodynamics of the system. You also assume that since you have local equilibrium, that the diffusion coefficient and the mobility satisfy a local Einstein relation, which connects the two. So the two are not completely independent and are connected by the second derivative of the equilibrium free energy per unit volume. And then you have to supply boundary conditions. So the boundary conditions can be seen, they have to be posed in this way, that the chemical potential is equal to the first derivative of the equilibrium energy evaluated at the density, at the corresponding density. Okay, so this is the very general setting. And we shall also assume that the stationary solution is unique. So this is the solution of the equation when the time derivative vanishes. And so the characterization of non-equilibrium systems is the fact that you have a current flowing through the system, while you can define a macroscopic equilibrium in the case when there is when the current vanishes. And in a case in which you have a stationary state, the external field counteracts the effect of the boundary chemical potential, and in fact they are related by this expression that is essentially the the ratio of the diffusion of the mobility times the gradient of the stationary solution. So you see, in our context, the stationary equation has essentially the same role of the equation of state in equilibrium. And you can define also a non-equilibrium free energy or entropy, for example, in the case of the simple exclusion principle, the system, the two things essentially coincide. And then it can be defined as a solution of a certain Hamilton-Jacob equation. But that is not the thing that I want to use. The current, the total current of the system can be can be split into two terms. One which is symmetric on the time reversal, and the other one which is asymmetric. So, and so if you write this in this way, then you see that these two you can show, and this is actually the only result I use of the macroscopic fluctuation theory, but there is no probability in this talk, that the Hamilton-Jacob equation is equivalent to an orthogonality relationship between the two types of currents. Then you can consider an energy balance. And the work done by the environment on the system in a certain time interval is expressed by these two terms. One which is connected with the reservoirs, which is the second one, and involves the current and the chemical potentials. And the other one is the work done by the external field. Now you can rearrange this expression by considering, by fixing some solutions of the hydrodynamic equations and with some initial condition. And using this Einstein relation, the boundary conditions and application of the divergence theorem, you find that you can transform this total work as the difference between the free energies plus the dissipation part. The dissipation part, you see, it has the structure of the Ohm's law, because it's quadratic in the currents, and the inverse of the mobility in the case of an electrical circuit is just the resistance. And F is the equilibrium free energy function. You see, due to the orthogonality equation, the relationship, this equation is the second term can be written as the sum of two positive terms, and this will be used in a moment. You see, because from the above expression, you can obtain the Clausius, one form of the Clausius inequality. And but this equation, if you want to consider this inequality, if you want to consider very slow transformation, so which in the limit lasts for an infinite time, doesn't carry any useful information, because the dissipation, you have an infinite energy that you dissipate to keep the system out of equilibrium. So the work will become infinite. But you can define the normalized work in which you subtract from the total work the part which describe the dissipation in the stationary state. So this is the expression they get, and so you get this is I mean, if the system relaxes exponentially, this term here with the symmetric part of the current, it's always finite, and actually for very large times it will go to zero. So you have for any finite time renormalized work which is natural in this scheme, which is larger or greater than the difference of the energies. And actually, this renormalized work, you can show that if this part, in fact, for big T going to infinity, this dissipation part goes to zero, because I mean, it's you can make a computation of order of magnitudes. And actually, in the infinite time limit, the normalized work will be equal to the difference of three energies between the initial and final states. So, and this is perfectly in finite terms. The part that we have subtracted, actually, this idea that you have to subtract something, it was in a paper of Ono and Paniconi of 1928, if I remember correctly, in which they called this heat, or this dissipation that we have subtracted, they call it the housekeeping heat. Okay. So now we have to analyze transformations over a large time interval. By slowly varying the boundary conditions and the external grid. So you introduce a dimensionless, you do what you do usually in adiabatic analysis. So you introduce parameters, so a dimensionless time, and the protocol transformations therefore is defined in terms of the external drivings, depending on this dimensionless time. And so I introduce this notation, and then you can rewrite the hydrodynamic equations in terms of this notation. And now you consider the fact that the time tau that you have introduced is very large with respect to the relaxation time. So for each value of S, the system has the time to relax and essentially be in a stationary state. So we try to develop the solution of the scaled hydrodynamic equations in powers of 1/2. So this R is just the first correction to the stationary density, and this G is just a correction to the stationary current. Now these quantities, so you get a linearized evolution equation for these first order corrections, which are written here, and which are rather obvious. Now you rewrite our the expression of the work that I introduced at the beginning. So it was, you rewrite this expression here in terms of these scaled variables that I just introduced. And then you start developing in powers 1/2. And then you find that the first non-trivial relationship, you can get an infinity of relationships. The first non-trivial relationship gives you the difference in free energies between two stationary states in terms of the first order work of the external field, of the first order work of due to the reservoirs. And there is a third term which depends on the fact that if you have your mobility, which depends on the density, then this changes with, for example, with the increasing of the density of the thermodynamic variables, and so you get a term. But if you consider a transformation through equilibrium states, the third term does not contribute because the big J's are always to be evaluated in a stationary state. So in order that this, the right-hand side, so you have the left-hand side that is independent of the transformation. And the right-hand side, which is where the protocols appear explicitly. So in order that this relationship would be consistent, I mean, this is the form of this, of the right-hand side has to be of this type, and where A is a quantity not explicitly dependent on time, and in our case, this is just the free energy, the equilibrium free energy, which depends on S only through the very slow variation of the chemical potential and the external field. Now you can obviously solve the linearized equation in terms of the Green's function in any dimensions, and then you get this expression, which are in this formula 26. Okay, then if you take as your pair of variables the field and the chemical potential as our state variables, and a transformation corresponds to a path gamma in infinite dimensional space, and then the right can be represented as a line integral of this form. I suppress all space integrals which are involved, and take into account that the stationary solution depends on time only through lambda and E, and then you separate the two time dependence, and you can obtain an explicit expression of the coefficients A1 and A2, which is somewhat complicated, so I will not write it here. Okay, so I will consider some examples. So if you consider one-dimensional systems for which the fusion coefficient is constant, and you can put it equal to 1 and no external field, then the calculation of R is very simple. And the solution of for this for the first 1/2 correction to the stationary density is given by this expression. You see that the boundary condition on R is that it vanishes on the two sides of the system, and then you see that the current it has the same absolute value but the opposite sign in at the extreme of the interval, and so now you have this profile is not exactly stationary, and that describes for all the gas systems which fall in the class that I have in the class that I have considered. You see that the description that we have for quasi-static transformations is that the total integral in space of the current is 0. And so the two reservoirs at the two sides of the interval provide incoming currents, and according to their sign, there is an increase or decrease of the mass. So R is just a parabola with concavity upward and downward, depending on the sign of the of this derivative of time of the stationary solution. Another example, again, without external field, but for which the calculation is rather simple. So we are considering a transformation, no external field, but in which the chemical potential at the two sides of the system, at the two extremes of the systems, evolve independently. Then you have at each instant of, for each value of S, you have a stationary solution, which is now linear on the space variable. But you can still easily calculate the variation in the thermodynamic variables and the variation in the current. And now the current entering or leaving, the infinitesimal currents or entering or leaving the system are not anymore symmetrical, so they don't have the same absolute value, but the total integral is again 0. So we get a rather detailed picture of what quasi-static transformation is. Now, another example where the calculation is slightly more complicated, but in which I introduce a constant field. So you have equilibrium states, but which are not homogeneous, because now the external field counteracts the effect of the boundary terms. And but still, now let's see this. So the description that we have is rather different from the one proposed by Calvin. He says that the quasi-static process is defined in terms of a dense succession of equilibrium states, because they have to alternate equilibrium states with the states out of equilibrium. So it's some dense sequence on this scaled variable, while we describe it in terms of this first correction to hydrodynamics over long times. But now let me comment on the formula from which we started. I mean, this formula clearly introduces in terms of this first correction to hydrodynamics, but the formula is exact. Introduced some equivalence because all protocols, once you fix the initial and final state, we give the same difference in the free energies. Now, at this point, that this reminded me of Clausius, especially the fourth memoir. So let's talk for a few minutes about Clausius. I'm sorry, I'm some difficulties in speaking because I'm taking a drug which for health problems that gives me these difficulties. So let's speak about you see, in fact, I always asked myself the question, how did Clausius get the idea of entropy in a pure thermodynamic setting? Entropy is a notion which carries some mystery in it, as was emphasized by several people, but in particular by qualified opinion that I'm going to cite. So there is a quantity called entropy in information theory, which measures the content of information or a message. The story tells that such a terminology was suggested to Shannon, the inventor of the theory, by the famous mathematician John von Neumann, with a comment. You should call in entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name. So that it already has a name. In the second place, and more important, no one really knows what entropy really is. So in a debate, you will always have the advantage. So now there is a fourth memory of Clausius by the title On a Modified Form of the Second Fundamental Theorem of the Mechanical Theory of Heat, which is very illuminating on how the idea of entropy emerged thermodynamically. The leading idea is that there exists a quantity. You see, he concentrates not on states, but rather on transformations. And the leading idea is that there exists a quantity called the equivalence-value of the transformations. He defines two transformations equivalent if they can mutually replace one another. And in fact, in his ninth memory, he would summarize the two principles of thermodynamics as follows. The whole mechanical theory rests on two fundamental theorems, that of equivalence of heat and work, and that of equivalence of transformations. You see, it's a very modern way of reasoning because essentially introduces entropy as an invariant which classifies, which denotes a certain class of transformation, which is invariant under the change of the protocols. So here I cite some, well, I don't want to read it in detail, but well, here is where he defines, well, he analyzes the Carnot cycle where he considers the fact that transformation of heat into work and at the same time that heat goes from higher temperature to to a lower temperature, it may be regarded as phenomena of the same nature, and we call two transformations. We can mutually replace one another equivalent. Once you have understood that, then it proves the Carnot theorem, the fact that on a cyclic process is the integral of delta Q over T is equal to 0. Now, why he thinks of the expression? In fact, he says, well, we have now to find the law according to which the transformations must be expressed as mathematical magnitude. In order that the equivalence of two transformations may be evident from the equality of their values, the mathematical value of a transformation to determine may be called its equivalence value. So this is the German word. Now, how he gets the form of this equivalence value? He thinks of a transformation of heat into work. And then he says, of course, well, that is his intuition. The transformation of work into the quantity must be proportional to the quantity of heat produced, or work into heat, I mean. And besides this, it can only depend upon the temperature. So he writes that it is of the form Q times a universal function, F of temperature, that he will identify later as the 1 over the absolute temperature. So I think, you see, the equivalence of transformations in the case of reversible transformations of equilibrium states is limited to the reversible transformation. Here, the equivalence is established on the one way you go a little bit out of equilibrium in every transformation. So you see, in this way, you have a dissipative context in which you can always establish an equivalence of protocols, and this gives you both the variation of the free energy between these two states of the equilibrium. That is again the problem of this equivalence value is again given by the equilibrium functional, and which is equal. And this I think shows more or less the correctness of our choice of the normalized work, which is also equal to the normalized work. Now, since I've mentioned several times the macroscopic fluctuation theory, here are some reviews. There are some reviews by us, a beautiful review by Bernard Derrida, and there is a recent review by Pedro Garrido, which has a somewhat different flavor, and it's very analytic and treats at the same level both diffusive systems, also reaction diffusion systems. So in this work of our work of 5 years and a half ago, by us there is something on this infinitely slow transformations that is not in the reviews. And on these remarks that I've introduced today, I've just written a short note that I will make available shortly. Okay, thank you very much for listening to me, and excuse me for some difficulties in speech that.
Thank you, Gianni. It was nice talk, of course, as usual. Any question or comment that someone wants to share? Let's see if someone. Well, I have a question. That what about to do some thermodynamics? How to count microstates? Is going to be possible at some point, or is impossible?
Well, I mean, this argument that I've given is based on hydrodynamics.
Mm-hmm.
So the point is to justify macroscopic equation of evolution. And I mean, Joel touched a little bit on this subject, and
right.
So I mean, I for the argument I gave, they are essentially macroscopic because I didn't use any probability. So they are thermodynamic at the level of mesoscopic description.
Okay, thank you. Any question? Okay. The Hal is asking some question. Hal, please.
Yeah, thank you, Gianni. It was very nice seeing you again. So as far as I understand, can you hear me?
No, I don't see you.
Yeah, you don't. I see you, but you hear me. So I understand that you studied 1/tau correction in this formalism, and you obtained some new exact relations like equation 24. So are these new equations do these new equations reduce to something which we knew already for equilibrium cases, or are they still new for equilibrium cases too?
Can you repeat the question? Because
so you have these relations like equation 24.
Yes.
So if we restrict ourselves to equilibrium cases,
yes,
are these relations something new, or do they reduce to something we already know?
Not that I know, because I mean, the advantage of considering diffusive system is that I mean, you have a detailed description of the driving.
Yes.
And in general, for any reversible transformation, you don't have it. I mean, at least I didn't find in the literature.
Okay. So you don't see anything
formula,
like.
I think this formula is really new, and you can derive other formulas by going to higher order, even 1/2. And this will involve derivatives of the equilibrium, free energy or entropy.
Okay, yeah, thank you. Very interesting.
Thank you. Any other question? Well, if no, I have to thank you again for your participation here, and it was a great pleasure to see you and to listen you.
Well, thank you very much for
inviting
me.
Okay, thank you. Then
in the past, I wanted to visit Granada. For some reasons, we didn't happen, but hopefully.
Well, hopefully next year or this fall, maybe we can meet. Thank you very much, Professor.